Good afternoon. So let us start. Today is the first laboratory class for compiler. So we understand that in theory we didn't cover anything. That's why in this laboratory, so I am going to introduce with you some of the system concepts that will be useful for us, and also the assignment that we are going to give you is not actually based upon or related too much on the compiler. Yes, there is relation, but not too much, so that you can able to do that one. So let us start. So these are the some of the basic things which will definitely know in details in your architecture class, which is going in parallel in this semester. Nevertheless, for our purpose to understand system little bit, so that what you are doing is basically designing the compiler. So you should know that what is the system, and accordingly you can plan, because finally you wish to generate the target code which is specific to some hardware. That's why we are having some slides on that one. So in order to know your hardware, so the hardware, for example, I have taken, so the processor is Intel Core TM i5 4570 CPU, and it says that 3.2 gigahertz is the speed of the processor, and max turbo frequency is 3.6 gigahertz. So here you can see that there is a small difference. Here it is 3.2 gigahertz, and here it is 3.6 gigahertz. So the reason specifically for this Intel kind of processor is that they use one concept which is called as the hyperthreading. So in short, I will explain you with some diagram in next slide. Next, in my system, there are 4 cores, and it says that at most 4 threads are allowed. But definitely, if you go for some thread level programming, like say OpenMP or OpenACC, then you can generate more threads than these 4. That depends upon how many threads you wish to fork or you wish to generate, that you mention, and those many number of threads will be generated. But it says that as per the architecture, it supports 4 number of threads. So you will get optimum performance if you use 4. But if you use more than that, then because of the context switch overhead, so there might be some loss of efficiency. You may not get the required amount of efficiency, or in other way, your program may not scale as you keep on increasing the thread. That is possible. In my system, from where I have taken this specification, so memory is 6 MB smart cache, and main memory is 4 GB currently, but the system has a support that maximum it can go up to 32 GB. So which means I can add more RAM, and up to 32 GB RAM I can add to my system. The software relevant to our class is operating system is GNU Linux. It is 64-bit and x86 64-bit system. Apart from that, the software which is there is GCC. It's the compiler for C, C++, and currently it supports the Fortran also. Lex or Flex, and YAP or Bison. Now, mostly we will be using Flex, which has little advantage over Lex and Bison. That we will discuss on the next week when we will discuss the lexical analysis and parsing part. So once you will have your system, I will request you to quickly check whether you have a support for GCC compiler or not, because some basic installation of say Ubuntu does not support GCC. So if it is not, then please install the required package, and also please check whether the Flex and Bison is there or not. If not, then again you have to update, but all these softwares are free, and you can actually update that package. But if you do not have the Flex and Bison right now, no need to worry about that one. When we will have a class on this Flex and Bison, then I will tell you the exact command that you need to fire from the terminal in order to check whether your system has a support for Flex or Bison or not. If not, then what to do. Okay. And on the last class, the question came that if my system is Linux, it's fine. If my system is Ubuntu, that is also fine. So only thing, the operating system should have the Linux. It will be 64-bit because you will understand today itself that there is a dependency, and the kind of register we will be discussing is of the 64-bit system. Okay. The language, it is C++, and I believe you are familiar with this one. In order to know your system, you can open one terminal, and then from the command line you can fire this command uname space -a. So this -a indicates all information. If you just type uname, then it will tell the flavor of your operating system, Linux or whatever it is. And if I say -a, then it will print everything. So this is the Linux system. The name of the computer was in my name, that's why it's Proloy. Then what is the software installed, and the full specification. Here the version of the software along with what was the date. So Wednesday, October 15, 2014 was the date when the last software was updated. It's x86 64 supports for x86 64 GNU Linux. That is the information. If you used to know about your CPU, that is CPU information, then from the same terminal you can just type cat space /proc/CPU info. Then it will scroll up mostly because a lot of informations are there. I believe nowadays most of the systems are having more than one processor. So corresponding to each processor, there will be entry. So it is not complete. As I mentioned that there are 4 processors. So similar to this, it is information for processor ID 0. So similar to this, processor 1, processor 2, processor 3, all will come. And what is the model name? What is the cache size? And what is the core ID? Mostly this core ID and this processor is same. How many CPU cores are there? So all those information along with the address size, 36 bits physical and 48-bit virtual is there. So cache size is 6 MB. In the previous slide, here I mentioned 6 MB smart cache is there. So regarding the main memory address, it says in my system actually, it is 36 bits physical, 48 bits virtual or logical, which means the width of any x86 64 address register is 64 bit, but the most significant 17 bits are either all ones or all zeros. So the logical space of any process is 48 bits. Depending on the model of the CPU, 48-bit logical address is translated to 36 to 40 bits of physical memory, main memory, and from there you can have an idea of the memory address. Now, if I look at the system, overall the CPU chip is looking like this, which is inside this pink rectangle is called as the CPU chip. And in this CPU chip, actually, it is the single core. This red square or rectangle indicates the CPU. Inside this part is actually the register file. It interacts with ALU. You know the full form of this one, arithmetic logic unit. It's bidirectional interaction, which means ALU computes, it sends the information to register, and then register sends the information to ALU, like that it goes. And this total red rectangle interacts through other peripheral devices using the bus interface. So first there is a bus interface, and then the bus interface is connected with the system bus, and then through that system bus it connects to other devices. Now when your computer is with, say, 2-core or multi-core, then the addition or extension that will happen here is the size of the rectangle will keep on increasing, and this red rectangle will be duplicating. So if there are 2 cores, then this rectangle will be twice, each indicates 1 core, and each of them will interact with the bus interface first, and along with the via the bus interface it will interact with the system bus. Okay, so here in this slide you can see that the memory bus is interacting with what? So here is my core 1 and core 2. So this pink rectangle is actually the red rectangle in my previous slide. Here, the red rectangle. Okay. Now there are 2 cores. That's why core 1, core 2. As per the ID, it will be core ID 0, and it will be, say, core ID 1. Along with that one, some cache at level 1, that is why it is L1. Then at level 2, that is why L2 is there. And you see in the from the previous slide, this complete red rectangle is interacting with the bus interface. Here, this is the memory bus. It is interacting with that bus. Now through this bus, it is interacting with the main memory. For my system, I mentioned 4 GB is my main memory, which can be extended up to 32 GB. It is also interacting with the DMA, so direct memory access controller is there. Then through IO bus, IO controller is there, and IO controller is interacting with say, secondary storage. If there are multiple storage, then disk 1, disk 2, it is interacting with the mouse, and then graphics, video, and then network. So it is interacting with that one. And here this part is actually called as the CPU. Okay. Now inside this CPU, if we look or if we zoom in, then we will see that there is one ALU, arithmetic logic unit, and floating point unit. 2 separate units are there. And for arithmetic logic unit, there is GPR, which means general purpose register file. And for floating point unit, floating point registers are there. The basic difference is that, as you understand from your knowledge of C programming also, that the number of bits or bytes required to represent an integer and to represent a floating point or double is different. Also, their interpretation is different. Usually, to store the mantissa and the exponent part of the floating point unit, you need to have higher precision information. You will store higher precision information. That's why usually the number of bits for FPR is higher compared to GPR. There is controller. So to control that which process will go or will be executing in ALU, which will be executing in FPU, like that. And other registers and latches like a program counter, IR, PSW, stack pointer, etc. is also there. Now here is one interesting observation you can see. Initially, when I have shown you that there is only one ALU inside this core, which is interacting with the GPU, which is interacting with the register file GPR. Then whenever there is some processing, the processing or computation will take place in ALU. Now, if we have along with ALU if we have floating point unit also, then floating point related computations will be bypassed to floating point unit, and arithmetic and logical computations will go to the arithmetic unit. Let us assume one situation that in your program there are some arithmetic and logical computations as well as some floating point computations. And if I assume that those two computations are mutually independent with each other or disjoint, which means that output of ALU will not depend on the input of say a floating point unit and vice versa. So there is no data dependency. If it is, then instead of utilizing ALU for the arithmetic and logical computations and then FU, means one after another or serially or sequentially, what if I know that for sure I know that there is no data dependency. So what if I send the arithmetic and logical computations, which does not include floating point operation, to ALU and floating point operations to FU. Then simultaneously or concurrently, they can be executing in two different units, right? So when I say simultaneously, then this is called as the SMT, whose full form is simultaneous multi-threading. Now you see one situation that individually this ALU has a speed of computation and FU2, FPU2. If it is the case that I am sending one part to ALU and simultaneously I am utilizing FPU, then definitely I am achieving some speed up on top of what is allowed as per the processor, right? That is the reason why you will see that max speed and the speed of the processor varies a little bit. This is a concept given in Intel and this is called as the hyper-threading. So you are utilizing the simultaneous multi-threading, one in ALU, another in FPU concurrently, by understanding that there is no data dependency, and that way you are achieving more speed up compared to what is allowed, that is 3.2. And Intel says for my system, this way maximum you can go up to 3.6. It is not the case that you will always get say double speed up or very high speed up. There are other dependencies also. Also there is one law which is called as the Amdahl's law that actually controls, and that says that if not significant part can be parallelized or say can be allowed to execute simultaneously or concurrently, you may not get that much speed up. Nevertheless, this is one concept used by Intel processors, and that's why you will see that there is a small variation in the speeds, and the hyper-threading concept is used for that purpose. Now, Intel 64-bit registers will be using 4 different GPR, general purpose register, floating point registers, multimedia extension registers, and this is called as the streaming SIMD extension registers. So the general purpose registers, they are 64-bit registers, and in total 16 such general purpose registers are there. All are integer registers. They are named as RAX, RBX, RCX, RDX, RSP, RBP, RSI, RDI, and R8, R9, R10, R11, R12, R13, R14, and R15. Each of them has a specific purpose. Mostly they are devoted for that one. I will go to their purpose and when we will discuss some example, then we will see that actually the purpose is being served when the program is in execution. In the floating point registers, it is 8-bit registers. So you see that the number of bits are higher. 8 such registers are there. They are named as R0 through R7. Now MMX multimedia extension registers, there are 8 such registers. All are 64-bit SIMD registers, single instruction multiple data. Starting, they are named as MM0 through MM7. So XMMS, that is an further extension of this MMX. You see that the number of bits for MMX is 64-bit, but if it is required to go for floating point calculation, so we need higher precision. That's why 128-bit SSE registers are there. The full form of SSE is streaming SIMD extension registers. They are named as XMM0 through XMM15. 16 such registers are there.
So
apart from that one, yes.
So can you repeat those MMX?
So which one?
MMX, third.
Which one do you wish to make?
MMX.
MMX.
Yeah.
So MMX is the multimedia extension registers. So there are 8 such registers. Each of them are of 64-bit. They are named as MM0 through MM7. And you here you see that the number of bits are 64-bit. So for floating point calculations or high precision calculation, we need some other registers. 16 such 128-bit registers are there. They are actually streaming SIMD extension registers, in short SSE. They are called as XMMs. So XMM0 through XMM15. Okay.
Yes, sir.
So apart from that one, few other special registers are there. 64-bit R flags, 64-bit RIP, program counter registers, segment registers, control registers, debug registers, etc. So here is the usage convention for the GPR, general purpose registers. They are 64-bit registers. So RAX is mostly used to return value from a function. RBX is used for polyset. RCX is used for fourth argument to a function. RDX is used for third argument to a function. Also, return value from a function. RSI is used for second argument to a function. RDI is used for first argument to a function. RBP is the polyset. This is also used for base pointer. Okay, RBP. RSP is the hardware stack pointer. R8 is fifth argument to a function. R9 is the sixth argument to a function. R10 is polyset. R11 is reserved for linker. R12 is reserved for C. R13, R14 and R15 all are used for polyset.
So what do you
Function
mean by
return address is at the top of the stack, so that
Sir, what
when
does
you
callee
return
save
from
mean?
that function, I will come to that. So that when you will return from that function, then you can read that one since it is on the top of the stack. Yes. Anybody has a question?
Yes, I was asking what does callee saved mean?
So, okay. So regarding this callee save, what happens? Let us assume a situation. Okay. I will go to that example, but let me quickly go to one such example, then I will come back again. So here in this C program, if you quickly look at it, I will go into details later. So include stdio.h, define something, void selection sort, then integer main, integer 0i, integer data, and then you are entering the data. You are basically reading the data, storing in the variable data here, and then basically you are using selection sort. Then you are printing the sorted number. Simple program, right? Now, after the compilation, when the program will be in execution, then what will happen? The program execution will always start at this point, that is int main. Then this variable declaration is done already. During the execution, actually, what will happen? So first it will start reading the data. After reading the data, it will call the function selection sort. Now you see that I am in execution in function main, but then I see that there is a function called selection sort data with two variables, data and number. I know that selection sort is there because I declared this one here, void selection sort here. Now this selection sort is here also, here it is defined here and declared here. Whenever there will be a function call, then I have to jump from this point to this selection sort point. So I am calling the function, right? Now when I am calling the function, then what will be the set of actions I have to do? So first of all, I have to save the state of this program. So this main program or main function actually was in execution. So up to which statement I have executed and what are the values for the variable, say no or I or data max number, up to this point I have to store that information somewhere. So the function information first I have to save. After saving that function information, then this data, which is the first argument, and the no, which is the second argument, that information I have to load, and I will jump. Calling the function means I will jump at this point to this selection sort function. After entering to this selection sort, the data that I have taken as argument 1 and no that I took as argument 2 will be copied here. Then I will keep on executing this whole part. After execution is over, then from here what I will do, I will go back. I will go back and resume my computation starting from here, right? So at this selection sort, I am jumping to that selection sort function. I am executing all the instructions of the selection sort. Once the execution is over, I am jumping back or coming back to the main function at this position. When I will come back at this position, then all the states of this function that I have saved, I need to get back that one. After getting back that one or restoring that one, I can keep on executing the function main, right? So after restoring all those saved information, if I start executing, then as if everything is same as before the call of the selection sort, except the situation since this data was called by pointer, so the content of the data will be changed. But if you look at the content of, say, no, content of I, content of say other machine states, actually everything will be same. That's why when I am, say, having my registers, then few registers I will dedicate to save that information, so that when I'll come back, then I can restore my system state for the next execution. Is that clear
Okay,
now?
sir. Sir, I have one more doubt on this. Now,
Yes.
in case we go for recursion, then we do many more function calls than the number of registers here.
Just a
So,
yes, tell me.
sir, like in case of recursion, we have multiple function calls. Like it can exceed 1,000 times or something.
Right.
So we don't have enough registers to save that many callies, right? So what do we do then?
No, that is a very good question. But first of all, when you are calling recursive function, then not everything is going to be stored in that register. Only the instance of the recursion which is in execution will be in the register. So you are calling one, and after calling that one, and then you are calling another one, then all those states will be saved. And after saving that state, it will go for another instance, and that instance will be actually called.
Okay. But we do not have enough space for like,
Proloy.
Yes.
May I
Yes,
just
yes.
intervene for a comment?
Sure.
I think we are getting into a lot of questions which are in our runtime environment module discussion.
Right.
These are all discussed in depth when we do the runtime module that we will do in 1-2 weeks only. So I think we can tell them to wait till that point. Right now, just get to know the architecture, not how the code will run on that architecture. Otherwise, eventually we will have to keep on explaining what is caller save, what is callee save, what is the stack frame structure,
Yeah.
what happens on recursion. All of these are the content of our runtime your module 6, which we normally do within the first couple of weeks of the lab.
Right.
So I think we can take it in that way. Otherwise, our current discussion is getting diverted. And these are very genuine questions which we need to discuss from the very beginning. They do not have idea about the stack frame organization. That's a score problem.
Yes.
So all these are coming. So we have to start from there and do it. Let us do it when we do the module 6. Currently, let us focus on the processor architecture only, because that is what they will need for the first.
I don't have also the diagram for activation record right now. That's why it is creating the problem also.
Yes. So let us plan week after next. Next week is holiday. Week after next, we will plan to do that runtime environment, and then all these questions will get answered in one go.
Okay, sure.
Piecemeal, it will just create more confusion for them. Okay. I think that is my suggestion. You please decide what.
Yes. That is a good suggestion. Yeah, actually, to all the students, the primary problem is that we are actually for this time being for this class only, since we just started actually. So let us go through this slide only. So all those questions which are coming is because of the fact that we do not discuss as of now that after say you generated the executable file, how it will load to the system and how it will execute. And when it will load to the system and in execution, then one instance will be created and how that will be stored. So those things we didn't discuss. But as you are asking the question, so we will plan that probably in the next class, we will have a quick coverage of that runtime environment. And as a complete module, so in the 6th module, it will come. So once we will finish our front end part of the compiler design, then that part will come at the beginning of the back end or the system design. Okay.
Yes, sir.
Okay, now we will do something for which those questions will not come. So from this simple diagram, you can see that this is the C program and this is the compiler. So on the source code, if you compile, then as of now, what you got is the executable file. So that is in one shot you go. But if you compile that one, then there is a possibility that from the C program, you can generate the assembly language program. And after that one, the assembler is also another kind of compiler which converts the assembly language program to machine language module it will convert to that machine language module. And after that conversion, this machine language module most of the time may not be able to execute, because there may be some library dependency for that machine language that is generated by the assembler. Once you will link all those library routines using the linker, then you will get the executable file. Now this executable file, up to this executable file, you will get in your hard disk. And the program is not in execution. Once here, this is actually your a.out. By default, the executable file in C or C++ you generated. Okay. Now, once you will type /a.out, then this a.out program will be loaded to the RAM using the loader, and it will keep on executing. This loader and linker are the system softwares. So we will not discuss these two parts, but this is the overall architecture. Okay. Now this C program, if you compile, I think some of you have already compiled using -c, small c option, then instead of a.out, you will get machine language module, that is the object file. This C program, if you compile using a flag S, -s, capital S, then you will get assembly language program. And from this assembly language program, if you compile using the assembler, then you can get the machine language module. And also this C program, if you compile with -e, capital E option, that is the C preprocessor, then you will get the preprocessed source file. Okay, so all this I am going to discuss using the system. So I am coming out from here. I am sharing my Linux machine. Okay, so do you able to see my terminal?
Yes, sir.
Okay, very good. Now what I am telling, you see that this is, I already wrote that one. I am showing you the content. So this is a simple C program. You can see int main, then int a equals to 10, return 0. Now you see that since there is no printf scanf, so I need not have to include stdio.h, and this program will compile. So if I say this hello 1.c, then it will compile, it will generate a.out. Okay. Stepwise, what I can do, if I execute this one also, it will execute, but since there is no printf statement, you cannot able to see that one. Okay. Now, if I go stepwise, cc, then what I am doing, e hello 1.c, then it is printing something on the terminal. If I store this one to say hello 1.i and open that hello 1.i, then you see your program is here. You can see this program, int main, int a10, return 0, and here hello 1 build. So these are commented. This is not much of our importance. This much is there. Now let us see another variation of our real hello world where we used to print. Has include stdio.h is required because we have a function printf. The prototype of this printf function is defined in stdio.h that we learned. That's why we need to include stdio.h. The variable, other variables are same. 2 lines are extra compared to the previous version. I incorporated one printf statement here. So variable a is assigned as %da, and since I am using one function, so the header file for this function I included, that is stdio.h. Okay. Now, this simple program, if I compile and print, then you can able to see that print statement. Variable a is assigned as 10. Now, if I compile using that -e, so I am using C preprocessor, I am redirecting and storing to hello2.i. Okay. Now I am opening hello2.i. You see, so many lines. At the end, I am going by giving $. At the end, you see that int main, int a10, printf return 0. The actual code is here. But before this one, everything is from stdio.h. So you remember from your previous class, so this kind of has include, has defined, those macros are being replaced during the first stage, that is pre-processing stage. So if there was some defined statement, so corresponding to that define, all the variables will be changed to its corresponding value. So here the content of stdio.h is placed here. You might be wonder that whether this much function is required for printf or not. No, this much is not required. But I mentioned stdio.h. So whatever is there in stdio.h is being included here, including the function for printf. Okay, so stdio has a lot of functions like scanf, all the reading and writing operations. So you can see here fputs, and then only puts, then unget c, so fread, those information. So you are it is putting all those together here. So I am expanding using the preprocessor. Okay, so that was one step. So in order to check that whether it is preprocessing or not. Next, I am generating the assembly language code. You have seen that if I just type cc hello1.c, then directly a.out executable will be generated. Now if I give -e, capital E, then it will generate the preprocessed file. I can show you that on hello say 2, which has the printf, on .i, on that one also I can compile, and it will also generate a.out. Okay, so that is preprocessed. That is also correct as per the syntax. Now if I execute this one, it will print the same thing. Okay, now if I compile to generate the assembly language code, I am doing it for the first one, say starting from C, but I can start from I also. So this C is generating one file hello world.s. So please note it down. So the flag I have to give for the compilation is capital S, capital S. And by default, it will generate the assembly language code in small s. Okay. Now, if I compile second one, hello2.c, it will generate hello2.s. Okay. If I open this hello1.s, then here I am getting the assembly language code. This is my assembly language code. So one assembler can able to read this code, and then it can translate to machine language. Now up to this assembly language code, so I can think of that it is compatible as long as there is an assembler which can generate the target code corresponding to one architecture. Okay. Now, if I look at the content, so this is hello 1, this is hello 2. So you will see as per the content, the difference was in 2 lines. One, I included that printf statement. Yes, I included the printf statement, and I included the stdio.h header file. Okay, because of the inclusion of the printf statement, you look at this line, call printf. So this line has come. This is my hello2.s. In hello1.s, it is little bit simple. So between this and this, there is no difference. So let me copy this part inside the main. Okay, and say this is my hello2. I am removing others because rest will be mostly same except one level. So the top one is from hello2. This is my hello1. You see that the similarity main will be there, so I am removing that. So this line, this line, this line, so all 3 lines, this line, this line, this line, this line, everything is same. Now this 16 and 10, this difference starts from here. So this is one difference. You can see the next line is same. This is one difference, and this is one difference because I am going to fire the printf statement. Okay, so these are the differences, and as you know, and I explained that from this s also, so this you can generate the hello2.s. If I compile, look, compile successfully, I can generate a.out. So that's here, although I am typing CC, but it is actually GCC compiler. So the GCC compiler contains the assembler, the C processor, and the C compiler within it. That's why using that I can able to do that one. Otherwise, I need to have a separate assembler. Okay. So any question from here?
Sir, what is the importance of the extensions?
Okay. So very good question. So as such, there is no importance. So the compiler is good enough or intelligent enough to understand that one. But one thing that if you do not use this say extension, then you may forget and you may mess up. Why you may mess up? I can show you. So here you can see that .c file, .i file, .s file, .o file, and a.out is there. Okay. Now there is a nice command in Linux that is file. After file, if I say write say hello1, then it says C source ASCII text. So you can read that one. Now let us assume I am changing it to C hello1.txt. Not say move, say copy, then file text. Still, it is telling that C source ASCII text. You see, here extension is .txt, here extension is .c. Now the problem is, if you write say hello1.txt, in future, do you able to remember that this is my C code? That is a question to you. If you say instead of writing .s, if you write it say .xyz, in future, do you able to understand it is an assembly language program? That is one thing, kind of documentation. Another is that this file hello1.i, hello, see I have shown you 1.s. They are telling that look, hello.i, that is also C source ASCII text. It is only the pre-processed file, so it doesn't make any difference with that. Now .s is the assembler source. It can understand by looking at the content, not by looking at your extension. That is also ASCII text. And when it is ASCII text, that ensures that you can safely open that one in any text editor. Now you think about this file, say hello1.o. It says hello1.o ELF 64-bit LSB relocatable x86 64 version 1 not strict. This is a binary file. I cannot open this one in any text editor. If I open this, then there will be a complete mess, because what the text editor will try to do, it will try to interpret each byte as one character consulting the ASCII table, and it will print some special characters, kind of using extended ASCII table. Okay, I do not wish to do that one here, but if you are interested, you can do that one in your system and you can see that one. It is same for a.out also. So ELF 64-bit LSB shared object and dynamically linked. So this dynamically linked also indicates that there may be some dependency with some other library functions which are available there. Now during the compilation, if you allow the option static, then the linking will be static, and you can port it from one system to another, which may not have the that much dynamic linking support. Now again, the final thing. Okay, so a.out.
రాజు అన్న వీళ్ళ దగ్గర ట్రై చేస్తే నాకు ఒకసారి
excuse me, is that a question? Okay, now same thing, the copy a.out, actually if I change to say hello extension, then also it will work. And then also if I say file hello, it will say the same thing. So extension is not that much important for the system, but it is important for you. Any other question? Okay, then I am closing this sharing and going back to the slide. Okay, now I am back to my slide. It is an example of a simple assembly program. As an inset, the program is written here. Void some function int a, it's an array, int n, then int I, sum equals to 0. For I equals to 0, I less than n, I plus plus, sum plus equals to a plus I, printf, simple function. And when I compile it to generate the assembly language code, so what will be printed? So I am not considering the header and footer part, only the corresponding this code, whatever is relevant, that I am pasting. It will be looking like this. What are the meaning of this? I will come with an example later, but this is just a glimpse. Again, so this is another example. If you have a source code, this program actually computes the value of pi, and there is a for loop. If you have that one, then in this program here, what you can see that since there is a printf statement, so I am including stdio.h, int loop and terms. Those are two variables, and two other variables, pi and sign. So in total 4 variables are there, all are local here. Then I'm printing enter the number of terms, scanf %d ampersand terms, pi initializing with 3.0, sign 1.0. There is a for loop for loop equals to 1, loop less than equals to terms, loop plus plus, pi plus equals to, this expression is there. Sign is with this expression, it is changing. After the loop, there is a printf statement and returns. So this source code, if I compile, okay, so this hyphen or W, capital WAL is kind of my habit. So if there is any warning in your program, then it will switch on all the warnings. You can ignore this one or you can keep it, because if you keep it, you may get some indication of if there is any warning message which may lead to some logical mistake, etc., that you will get an indication. Otherwise, you can remove this one. Okay, all this WALL hyphen WALL. It indicates all warning on. Okay, so hyphen capital S, then compute pi.c, assuming the last program, this program actually is saved as a file name compute pi.c, will give you compute pi.s. If I just compile to generate the object file, then cc minus s compute pi.c compute pi.o. It is generating the object file. And if I compile without any option like minus capital S minus small c or minus capital E or hyphen capital E actually, then it will generate a.out, that is my executable file. So today in this first lab and assignment, we are primarily interested about this .s file. Okay, so the compiler compiled and converted the .c file to assembly language program .s. So from this .s, we will try to understand that what is the relevance or what is the mapping for this .s to .c. That is our agenda for today. Before going to that one, let me tell you some of the conventions that are used for the assembly language instructions. So as you have seen that all these are nothing but the instructions: push L, move L, push L, sub L. So they are all nothing but the instructions, the set of instructions in the assembly language. So this push is similar to push operation in the stack. Move is moving or copying operation. So copy, there doesn't have any other copy operation. It's the move operation. Move means the copy. Then push, sub is the subtraction. I am deliberately missing the last character because I will discuss that later. Then move. Then this is the test, means compare. Then this is jump, less than equals to JLE. Then move, add. Then compare between two registers. Then jump when not equals to, that is JNE. And here call one function. Here call printf, that you can see. Pop, since there is a push, pop is also there. And finally return. So these are basically the instructions in the assembly language code. And corresponding to that instructions, so you will see at the end of this semester when the code generation will be done, that corresponding to that instructions, there is a machine code available, and you translate from that assembly language to that machine code, then you generate the target code. Okay. So as I mentioned that today's laboratory and agenda and assignment is on having a correspondence with the assembly language program and the C language program. After generating the assembly language program from the C language program using GCC compiler and say S capital S option, that is hyphen capital S. Now the conventions, those which are used for instructions in the assembly language, that move L, push L, so that you remember, right? So that says that the suffix, when it is B, it indicates that byte. The size of the data that it is dealing with is in terms of byte. So 1 byte or 8 bits. When it is W, then it is word, 2 bytes or 16 bits. When it is L, then it is long, which means 4 bytes or 32 bits. When it's Q, that is called as the quad word, that is 8 bytes or 64 bits. Please note it down that this BWLQ, whether it's a small or capital, so that doesn't matter. So so here all are small actually, but even if you see that capital is there, okay, then you consider that is small. So here all are small in the example, and in the following example also we will see that all are small. Here also it is small, but for the explanation I have used this BWLQ so that it is visible actually from distance, but all will be small. Okay. Now on the left hand side, 64-bit, so percent %RAX, you remember. So if this is 64-bit, then almost half, not almost, actually the half is the 32-bit, and 32-bit is called as the EAX. So whenever you will see that this percent EAX, percent indicates that next what is coming is the name of the register. So when it's percent EAX, then that is 32-bit register. When it's percent RAX, that is 64-bit register. Percent only AX is 16-bit. Percent AH indicates higher 8-bit of the 16 bits. Percent AL indicates lower 8-bit of the 16-bit. Similar to that, when it is percent R8, then it is 64-bit. Percent R8D, not 8E. So not E8. It is percent R8D, then 32-bit. Percent R8W, 16 bits. R8H, higher 8 bits of the 16 bits. R8L, lower 8 bits of the 16 bit. So this H is higher, L is lower. This L has nothing to do with this L, which is long. Okay. So this L actually is coming in the register, and this L is going as the end of the instruction, the assembly language code instructions. So the occurrence is in two different places. That's why you should not be confused. So global symbol, move Q. What is Q?
Welcome to week 5, module 21 of database management systems course.
Hello, PVD, are you telling something? Hello.
Yes.
PPD, are you telling?
No.
Okay.
Sorry.
So in the convention, global symbol, so move Q. So here again, the in actually the assembly, it will be the small one. Now this move, as I mentioned, it is the copy instruction. Okay. So Q, what is Q? From here, Q means quad word, which means 8 bytes or 64 bits. Then X is the variable. So the content of the X will be copied to the register RAX. Okay. So RAX, you have seen it is 64-bit RAX. So the content will be copied to RAX. When the instruction is move Q $56 %RAX, that means immediate. Immediate means $56 indicates the 56 value actually will be copied to register RAX. Then move Q %RBX %RAX. That is very simple that you understand that RBX will be copied to RAX. Indirect, if you give the parenthesis, then actually the content of this register will not be copied to RAX. Rather, the content of this register is holding the address. You go to that address or location, you fetch that data and copy to RAX. That is the indirect. So that has the similarity with the reading by address or pointer, where instead of the content of the pointer, you are basically going to that memory location whose address is stored in the pointer variable, fetch that data and do the calculation. So here it is also like that, indirect. Now base relative indicates move Q -8 % RBP, which indicates that in RBP, whatever value is there, you subtract 8 from there and copy to RAX. So all are for just convention and illustration purpose. That's why the register here is used, say, in all cases RAX, sometimes RBP, RSP, but it can be anything. I believe that you can understand. Now, offset scaled base relative. So this indicates percent RBX, percent RCX, 8 minus 16. So this offset scaled base relative indicates that from one location you skip a number of rows, and after skipping that one you subtract that one. This you can consider similar to that the two-dimensional array is stored as a row measure, and you wish to access a ijth position. Then how we will calculate? So one offset is there and one scaling is there. Scaling, that means it will be multiplied with this one, and then offset is minus 16, and this is actually the base. With that base, this bx, and the final value will go to the RAX. So those are the conventions. So corresponding to this, corresponding to that compute pi, the program here. So the assembly program which is generated is like this. So the name of the file is compute.py.c. This is the source file name. .section.ro data, read-only data section. .align 8 space 8 indicates align with 8-byte boundary. So these are the levels .lc0, .lc1, .lc7, because in between 0, 1, so 2, 3, so is somewhere else. So this, yeah. So LC3, 4, 5, 6, so all are present. It is like this. Now this string, what is the string? Enter the number of terms. Go back to the source code. So printf, enter the number of terms. So this is my string. So this string is stored as a label .lc0 and .string. Now .lc1, another string, that is %d, which is inside the scanf. Here I am reading that one. Okay. The third one, value of pi, it is also here, value of pi. So those strings are present. After that, .text, .global main. So main is a global name. .text actually indicates that code starts. The type of this global main, actually the main is a function. So that's why comma ampersand function. So main is a function. Then main starts with the label main colon WLFB0. So .cfi start proc, it indicates that start of the procedure. This .cfi actually full form is call frame information. So we will not go into details of that call frame information. Rather, we will focus only on the instructions for the time being. Those will be discussed later. So push q, the last one, suffix q indicates quad word. So 64-bit. %RBP base pair. So save old base pointer. In my example, as I mentioned, that for the selection sort, that again will come again. So I am saving that state, and then I am moving to another function. So in this case, what I am saving, because I have just entered to function main. Just after entering to the function main, so you have to understand, before the execution of the function main, the program, the processor or the system has one state. The system needs to save that state so that once the execution of your function main is over, then it will restore to that particular state. So that's why even at the start of the function main, it is storing that information. So the base pointer is being stored. Then CFI, we will skip those for the timing. Move Q. So quad word, you move from RSP to RBP. So the stack pointer is I am moving to the base pointer to set the new base pointer. Next, subtract word sub q $32% RSP. So $32 indicates immediate operation. So 32 is the integer that will be subtracted from the RSP. Why 32 will be subtracted? Because if you go back to the program, you will see there are 4 variables: loop, terms, pi, and sign. So in order to store those variables, I am creating the space. So create space for local array and variables. Here I do not have any array, only 4 variables. So 4 for each, into 8 for each, in total 32 bits I am subtracting. So RSP. Then move L. So move, this is long. Then dot LCO. So again immediate dot LCO. LCO is what? The string, enter number of terms, %EAX. EAX starting of the format string, first parameter. You remember from the register that I introduced to you, arrayX, return value of a function. And here in EAX, the starting of the format string, that is the first parameter I am entering. So when it is EAX, then you understand that it is what? 32-bit EAX, and L 4 bytes, 32-bit. So L I am using, you see. So it is L and EAX, so 32-bit. Then move Q, arrayX to RDI. I am moving, move L0. So the value 0 is assigned to EAX, 32-bit, but since it's 0, doesn't matter. Then I am calling printf function. The moment I will call printf function, since first parameter is this .lco, which means enter the number of terms, then that will be printed. Next, I am moving .lc1, that is %d. Then I am doing the same thing here. Move Q, then move L0 EAX. Then I am calling ISO C99 scanf. So the ISO standard, the manual, all those data I will upload in Moodle. Okay. After calling that one, what it will do, it will read the value which is given as an input, and it will store that one in the variable. So first it will store in the register, then after that it will translate to the move to the variable. So like that, so many instructions are there. I am not going into details, just giving you a glimpse of this one. Details I will go for this one. Okay. So why I choose this one? Because there is a function call apart from the scanf and printf, which is also a function call for which this stdio.h header file is there. So for this selection sort, the same thing will be done. But before I go to that one, let us look at the source code first. So it includes stdio.h, define max number 100, void selection sort. So one integer array will go and another integer variable will go. This is my function int main. Please note it down that this comment part will be removed during the first phase, that is the lexical analysis, that we will discuss on the next class. The comment will be removed. Not only this double slash, but slash star, that will be removed, because this comment has nothing to do with the compiler. It is just for your documentation purpose. Okay. Now again, the declaration of the variables, 2 variables, integer number equals to 0 and I, then integer data max number, so which is an array, 100 data. Printf, enter the data, terminate with Control D. While scanf data, I am reading this data. Then I am calling the selection sort for sorting purposes. Printf, data in sorted order R. Then I am printing them so that it will be in the sorted order. Finally, I am putting putchar /n return 0. In the selection sort part, so I am defining one macro, has defined exchange x, y, z, z equals to x, x equals to y, y equals to z. This is a simple macro, and this is with the C program. I believe you are right now kind of master in C program. I am not going into details. So void selection sort, one array, another the number of elements is being passed here, and using that one I am performing selection sort here. Okay, so here there is an exchange. Again, I am not going into details, so you can look at it. Now, if I write these two as two separate files, so the main will be in one file like main.c, and this selection sort will be as another file, say selection cell sort.c. Then what I need to do, that I need to compile them separately, then I need to link them in order to generate the executable file. How I am doing? Again, this hyphen WALL is optional. You can remove that. I have a habit of putting that one. Hyphen capital S indicates it will convert to assembly code main.s, that we will discuss in detail. Then hyphen small c main.c will compile and generate the object file. Capital S hyphen capital S cell sort.c will generate the assembly code. That also we will discuss. Then hyphen small c cell sort.c will generate the object code. Now, if I fire cc main.c and cell sort.c, then it will generate a dot out by linking them. Okay. Or else, if you write everything in one file, then perhaps one compilation is good enough. But I will suggest not to use that one. And regarding this linking main.c, main.o and cellsort.o, there is a very nice way of doing that one, that is writing makefile, that we will discuss in our next class, next laboratory class. Okay. Now let us look into details of main.c and cellsort.c with an aim that all the translated or say compiled assembly code will be mapped to the corresponding C file. So we will find a correspondence. That way we will learn that what does that mean with the C code, because we are familiar with the C code but not with the assembly code so far. So this is one small diagram which says that using the library main file and cell sort, the linker actually compiles and generates a dot out. The file type that I demonstrated to you, if you write file main.c cellsort.c, it will say ASCII. So in one system it was showing ASCII English text, but currently the system I demonstrated, it will show ASCII C program file. For this, it will show assembly language text instead of English text. It will also show for main.s that ASCII assembly language code. But for main.o and cellsort.o and a.out, it will say that it is ELF 64-bit, elicible, relocatable, and what is the version. So all those things it will be mentioned. So this indicates again that up to this one, I can open in some text editor, I can look at it, I can read at it, or I can edit it. But this .o or a.out, which means object file or executable file, I cannot do anything. I mean, I cannot do anything by that. I used to mean that I cannot open it in editor and do some editing on that one, specifically the text editor I am talking about. So this is the assembly code for main.c first. So the name of the file, since two separate file was there, main.c and cellsort.c. So dot file main.c, it is the name of the source file. Section .ro data, read only data section. Then dot align 8, align with 8-byte boundary. Dot LCO, label of F string, first printf. Dot string, enter the data, terminate with Control D, similar to the previous example that we demonstrated. Dot LC1, dot string %d, dot LC2, string data in sorted order. So how many printf statements are there? So number 1, then number 2, then number 3, then number 4. So here, so this is for the first printf, this is for the second, this is for the first scanf, this is the second printf, this is the third printf. So those are being printed. Now the code starts dot text, again global. Please note it down, there is no a, bl, main. Main is a global main. Type So what is main? Main is a function. It's not a variable. So as the compiler class will progress, you will see in the symbol table the information we store, whether it's a function or it's a variable, what kind of, what type of it is. So all those information we store actually. Okay. Dot type main ampersand function. Main is a function. Now the content of the main, first again we will push forward, that is %RBP, the base pointer we are saving, so that we can move on to executing the main. Then move Q, so %SP, %BP, so RBP, RSP is going to RBP, set new stack base pointer. Next 416, last time it was 32, if you remember. So only 4 variables was there, 2 integer and 2 double. That's why 32 was subtracted. In this case, if you look at 100 integer variables are there, data, max number, this is 100, along with 2, number and I. So because of that one, so 416 actually was subtracted from the stack pointer. Again, do not go to visualize this one because it will be discussed in runtime environment with the help of one diagram of the activation record. So in the main memory, when it will be loaded, then from the stack pointer it will go down. That's why it is being subtracted. So that's why it is being subtracted. Then create space for local array and variables. Next move L long -8. This is indirect, which means in the base pointer whatever is there, you subtract 8 from there and initialize 0 there, so that number will be initialized to 0. Then I am moving LCO to EDI, the first parameter of printf. Call printf. So actually this will be printf. So call printf, then it will print the first one. Then jump JMP. This is the unconditional jump to L2, the level L2. Go to the beginning of the while loop. So in the while loop, so I am reading. So going back to the source code. So I am reading. So this is my while loop. In this while loop, I am reading. Okay. So here moving -8 RBP EAX. So I am making the space for the reading. Then CLTQ RAX, EAX is going to be the RAX, 32 bits to sign extension of 64 bit. I'm converting that one. Then shift arithmetic, SAL, shift arithmetic forward 2. So shifting by 2 bits actually indicates that I am multiplying NO variable with 4. So I am creating the value 4 multiplied with NO, and that value will be in RAX. Then LEAQ, okay, minus 416 RBP. Again, this is indirect, which means 416 will be subtracted from the existing base pointer RBP, and that will be stored in RSP. Then add Q. So forward. So 64-bit addition of what? RSI and RX, and the result will be stored in RSI. So data plus 4 multiplied with number, so which is nothing but, you see here. So data was an array in the source code. So data is an array of integers. Now with that, if I add 4 multiplied with NO, then it will indicate that ampersand data in O, and that is my purpose to store, because I am scanning, I am reading in the while loop, so to store that one. Then move L.lc1 again. So this is basically my scanf. So that LC1 is %D EDI. Then I am moving 0. Then I am calling the scanf function. So it will read. So compare -1 with EAX. If return value, so -1 indicates end of file, which means whether the input is ended or not. If yes, then you jump. So if not equals to, then jump to .L3. Where is L3? L3 is here. I'm going back. So L3 is, I will add 1 with the RBP -8, which is nothing but the NO. So I will basically increment NO. Now you see, RBP is not changing. RBP is fixed. Now taking the indirect operation, RBP minus 8 here, RBP minus 416 here, RBP minus 8 here, using that one, the content I am changing, and that content corresponds to NO here. The content corresponds to ampersand data here. So this corresponds, I am explaining. So I am not just explaining that, okay, jump to L2. But I am also mentioning jump to L2, which is nothing but the beginning of the while loop. That is what is I am establishing the correspondence between the assembly code and the C code, and that is required. Today when we will release the assignment, then we will give one C code. You are supposed to using the assembler, which means CC or GCC or G++ minus hyphen capital S C code, generate the assembly code, and you annotate that one, which means you need to add these comments using the hash. If you add this comment using the hash on the right hand side, it is the comment. So the same code, if I compile, then it will execute. But if you do not use the hash or comment it properly, if I try to compile to generate the executable file, it will not generate. So be careful that it should be executable. It should run. It should compile. At the same time, you will make the comment. So making the comment is the assignment for today. I will go to that one. But the same thing here, what I am explaining, you have to do this one. Okay. So after calling the scanf, now you have two options. Either there is no input, then you will go next. But if not equals to JNE means jump or not equals to, which means if it is not equals to minus L, before that one I did comparison. So after the comparison, what will happen? CMPL. So L means 32-bit, and that's why it is EAX. So after the comparison with -1, the result will be in the accumulator of the ALU. Next, when I will fire JNE jump not equals to, then it will look at the content of the accumulator and decide accordingly. Then by looking at the content, if it finds that 0, which means previously the compare operation yields or resulted equals to. But if it finds no, it is either positive or negative but not 0, which means that the previous comparison operator was not equal. That's why some residual part is there in the accumulator. So when I will do CMPL, then it will do the comparison at the accumulator, comparison of the register %EAX and with -1 actual value. After the comparison, this statement is over. Next, JNE, what it will do, when I will say JNE jump not equals to of what? So it will look at the content of the accumulator, and if the accumulator is a non-zero value, which means it is not equals to in the previous statement. So jump, otherwise it will not jump. Jump is going back to previous slide, .L3, addition of 1 with the -8% RBP. So which is nothing but addition of 1 with the NO variable. Okay. Otherwise, what you will do that, okay, reading is done, you move forward. So, and this LEAQ is less than, so this is the operation. Okay, so this %D, so data is going to be in RDI. And after that one, you call the function selection sort, and it will go to the selection sort function. In the selection sort, you perform the selection sort that will come next. Okay, but after calling the selection sort, these are the statements which belongs to function main, because we have two different functions. So separately we compile for generating the assembly language. So in this particular file, which starts with the name, the first line of this assembly code, file.main.c. In main.c, there is no code for selection sort, but calling the selection sort. After that one, this part belongs to function main, and also this part. So everything. So after that, the printf statement, etc. which will be in the function main. And here I am closing with the function main section dot EH frame a prog bits. Okay. Now in separate file there is select cellsort.c, that is the file name text. Similarly, it will start instead of main, it will be selection sort. Again, this type is a function. Again, this is a global function. Global means that it is not locally defined. Okay. The same thing means overall the concept of the function will be same here, but the content definitely will change. And here the content will change accordingly. Now you see that I am moving, so that exchange operation. So I am moving RDI, RBP, and -24, -28, -16. That indicates that the I plus 1, I minus 1, I plus 1. So exchange between these three variables. So those are being listed here with the proper comment. Okay, I'm not going into details. I believe that you can able to decipher it now. Okay, so this is what actually you have to do. So this is the entire code which is given. You should consult this one along with the other manuals that I will upload there. So there is no need for discussion on CFI directives. So we didn't make much progress on that one. So this CFI start proc, CFI end proc, CFI def, CFA offset, CFI offset 6 -16, CFI def, CFA register or .eh frame. You need not have to make any comment corresponding to this. If you wish to comment, it's fine. This indicates start of the procedure or function. This is the end of the procedure function. So if you wish to do this one, it's fine, but otherwise we do not want it right now since this is the first lab. Okay, so that's all about the discussion for this class. So now if you have any question, so please let me know. So again, I wish to say I will show you the today's assignment, but what we need that given one source code, something like this, the source code will be given to you, some simple source code. You need to compile using this -s option, capital S option in order to generate .s file. Then on this .s file, you need to annotate this one, which means you have to comment this. So comment will come after the end of each line with has, so that this .s file, when you will save, then at our end we can able to compile that one to generate the executable file and run that program. Okay, and during the process you should not only write, say for here, so moving say RSP to RBP, you should not write only this one. Okay, so for here you say for this move operation you should not write that moving RBP -8 or assigning RBP -8 to 0. You should not write that one. But what you need to write that corresponding to this operation, what is the instruction in C program? Here 0 is going to be NO. That is what is written here. So that is what is required from you. Okay. Now if there is any question you can ask, otherwise I will show you the today's assignment.
Am I audible?
Yes.
So you mentioned that we assigned 32 bits for storage, right? But we had 2 integer variables and 2 double variables. So why are they equally distributed? Should it be 24? Like 8 for...
No, you are talking about the content, the number of bits.
Yeah.
But here it is the point of the how many addresses they need.
Okay, so it is not based on the data type of the variable.
Right. Not that one. Say if the data, if the size of your data bus is 64-bit, okay, then this will be used for storing one say 64-bit data, and if there is one 32-bit data and another 64-bit data, then one will be stored here, another 32 will be stored in say 64-bit, but rest of the 32 will be unused because another 64 bits are there. So do I make sense? So if there is a requirement of 164, another 32, another 64, right? then 3 different memory locations are required. So one for this, one for this, and one for this. It will be depending upon the size of the data bus.
So how did you assign 32 for the 4 variables? I did not understand.
Which one? Full variables.
Yeah, you mentioned that you assigned 32 for the 4 variables, right? 2 were int and 2 were double.
Right.
Yeah, so how did you do that?
So 4 variables here, you can see there are 4 variables. So 4 variables was here.
Yeah.
Loop, terms, pi, sign. Okay, 4 variables. For this, I mentioned here in this code that this 32 4 variables. For this program, data max number 100 array of 100 integers and 2 more integers. So 102 integers are there. Okay. Now, now one point also remains there. So in structure, in class of your PDS, in structure, when there is a structure, right? And say that your memory is something like this. Let us assume that it is 32 bit of length. Now, if you declare one integer, say integer is of 32 bit, it's fine. It will be holding the entire 32 bit. Or say if I say integer will take the 16 bit, it will take the 16 bit. Then if you declare one character, so character means it will be 8 bit, right? So this will be the 8 bit character. Then if you declare one more integer, then integer will come here. On the other hand, if the same thing you declare 2 integers first and then one character, then one integer will be here, another integer will be here. Sorry, my handwriting is very poor because of I cannot able to handle cursor completely, and then character will be here. Now you assume one situation that after this character you have one more integer or something. That way, how much space will be required also depends upon the way you are declaring. If you remember that PDS class, inside a structure, the member variables, how do you organize those member variables? Based upon that one, corresponding to one structure, how many bytes will be stored will change. So here also, and in that case, based upon the system and based upon your declaration type, so this number may vary. So for 16 or say whether you are using 32-bit system, this number may vary. But whatever may be the value, that value will indicate that I am creating the space for local array and variables. And since you know how many array and variables in total are there and what are the data types, so based upon that one, you can have an estimate that probably how many bytes are required corresponding to one integer.
Yes, got it. Thank you.
Any other question? Okay, so then let me go to that assignment part.
Excuse me, sir.
Yes.
Sir, by when will the slides of today's class and also the last theory class be uploaded on Moodle?
I will do that today. Don't worry. I'll do that. Okay. So you know it is the start of the class. So initially, it's true that we are lagging a bit, but after that it will be very regular. I will upload so 3 slides along with some materials also and one assignment. Okay.
Okay, sir.
So this is the assignment I will upload in Moodle. You please check after say few hours, so you will get it. So what you need to do that the assignment, this is the first assignment. Actually, there will be 6 assignments. The first one is annotating assembly, and marks is 50. So this 50 actually doesn't mean anything at this point. So all will be scaled later. So these 6 assignments, 2 lab quiz, so it will be scaled. And as we mentioned that there will be a proportion, there will be a portion for the assignment as well as the lab quiz. So our suggestion is that you do your best for all the assignments in order to have a good grade. Today we are studying. Submission date is 2 weeks from now, because I don't know the exact number, but some of you said that they are coming back to the campus, and for this movement, travel, etc. They may need some time. And also next week on 19th we have a holiday. So it's Moharram as per the calendar. So we don't have any class on the next week. So that's why 2 weeks is the deadline. So translate the following C program using GCC or Linux, not or actually you read GCC Linux to assembly language program of x86 64 Intel 64-bit processor without optimization. Do not apply any sort of optimization at this moment. Use just this CC. As I mentioned, this is optional -WALL, but you give only the option -S and then file name ASGN. Okay, there is a typo. I think you can understand. So C program either ASS1.c or say ASSGN.c, whatever is the assignment. So in this program, so include stdio.h, define max size 100. Okay. So similar to some extent, I kept it similar with what we discussed in the class. Then void, insertion sort, then binary search. These two functions are declared here. In the main function, I am reading the number of elements first, and then I am reading all those elements. Then I am performing insertion sort. Then I am printing those elements. After that, after insertion sort, I am reading one more item to search, and using binary search, I am checking whether that element is present or not. If it is present, then I am printing that yes, it is present at this particular location. If not, then I am reporting that item is not present in the list and return 0. In the function definition of insertion sort, so 2 variables are the input. One is the integer array, another is just the integer. And then I am doing the insertion sort, this is simple one. And I am doing the binary search, this is also simple one. And what I am suggesting, rename the generated assembly file as ass1_roll.s. So this role is important, and it must be your roll number, because we go for a bulk download, and if the file name is similar, then there is a possibility that it will overwrite. So to avoid the overwrite, so it is not the name, but roll number is the best thing. That's why you please use this naming convention, otherwise it will be difficult. Where roll is your roll number, add comments for each of the assembly language instruction. Your comment should explain the functionality of the instruction at the connection to the original C program. Please make sure that your commented file can be compiled to generate executable file. Upload your file ass1_roll.s in Moodle server. That Moodle server, I hope that all of you have enrolled to that course, compiler, theory and laboratory. Okay, so theory for the lecture slide of the theory class, and laboratory is for the lecture slide of the laboratory class and the laboratory assignments. Theory section is for the theory class test. There will be 3 class tests, and laboratory session is for the 2 lab quizzes. There will be 2 lab quizzes. Okay. Comments without connection to C program will get partial marks. So partial marks varies from 0 to say 100%. Okay. So because connection is required, you know that, otherwise it will not make any sense. So any question from this assignment? I think it is pretty simple to start with as an assignment 1. Okay. So silence, I am considering. Yes.
Yes, so like I have all the specifications in my PC, but I have a AMD processor rather than an Intel one. So will that cause a problem?
I don't think that will cause much of a problem, but you can use some online platform, and you can say test it at there. Okay. But
Sure.
But if the instruction set is different, then it will be a problem in future for assignment 6 when we will go for target code generation. Okay. So you know that we are also trying and adjusting with the current scenario. Previously, what was the situation? Each student was allotted one laboratory computer, and in our department, as you know, that all the software lab computers are equipped with this Intel 64-bit system. That's why we are doing this one. But now the system is completely different, so we cannot. So first of all, there are heterogeneous system you have, that I understand. And another thing is that if you give something in say AMD and our TA do not have AMD, then it will be a problem. So that was the same thing Professor PPD also mentioned on the last class. Some of you may have Mac, but Mac has different instruction set, and our TA may find difficulty to access to Mac. They mostly do not have. I guess they actually do not have it. So if they do not have, then how do you expect that they can check your assignment in there? Okay, so it's a problem. Okay, so in this connection, so may I know that how many of you as of now are able to find a Linux system? So last time actually it was 27, I have seen. So again I am posting. Can you please like it to just get a vote? So if you have an access to online compiler or online system also, then please mention. You may have say Windows in your system, but you can access in online mode some Linux system some way. You please mention that. Okay, in the meantime, there is a post that, sir, you are going very fast. I am really sorry, but instead of posting, if you can pause me, stop me, sir, you are going faster, then it was helpful. Because you know, when I present, actually, I cannot able to see your post here. So I see only my screen. That's why whenever there is any question, don't hesitate. Just unmute yourself and talk to me, like similar, like a class, where you raise the hand. Instead of raising the hand, you just tell. So right now it has increased to 41, 14. So 14 has increased. Okay, that's good, but I suggest please look out for the possibilities around, so that you have the access. Otherwise, doing assignment will be difficult. Also, I suggest one more thing, that as PPD also mentioned, we are planning that assignment 3, 4, 5, 6 will be in a group of 2. So when you will form the group, so please be careful that at least one of them has the access to some Linux machine. If there are 2 guys, they are forming the group, none of them has the access to the Linux machine, then it will be a very, very difficult thing. Okay. So at least that way we can reduce. So as per ERP, as of now, 130 students are there. So divided by 2 means 65 groups will be there. If 42 students has the access, and few more if you can arrange, then it will be really good. Okay, but for today's assignment, actually you need only the only once you need to access to some Linux machine in order to generate the assembly language code. Then you have to do the annotation. Then you need not have much of the Linux machine. That
this one is good with the online.
Yes.
This assignment is good with online because there's nothing to work. Just build and download.
Sir, can you provide this ASS1.c file as a downloadable file apart from the PDF?
Okay, I'll do that. Yes, I will do that one.
Because sometimes if you copy from the PDF, then the new lines go away and it kind of gets garbled. So yeah.
Better I should write. I should say that okay, write one insertion sort, binary search, and then do this one. Okay, I will do that one. So that can be done. That's not a problem. Okay, I am. So we are done with today's